Right, thanks. So let's start now. So we have this P field F, which is the field over which we want to prove Sayre's mass formula. Then we have K, which is obtained from F by adjoining the P minus 1th roots of everything in F star. We have the Galois group G of K over F. And our proof of Sayre's mass formula went through this parametrization, the parametrization of all separable extensions of degree P over F. This was put in by natural bijection with a set of all G stable lines D in K star modulo K star to the power P in characteristic 0, or K plus modulo PK plus in characteristic P. Of course, the field F and K have the same characteristic, and it can be P, which is the characteristic of the residue field, or it could be 0, because F and K are P fields, right? And recall that E and D correspond to each other under this correspondence, under this parametrization, if and only if when I base change, or when I take the composite term EK, I get the extension of K obtained by adjoining the pth roots of everything in D or the Artin-Schreier roots of everything in D, depending upon the characteristic. Again, another thing which was fundamental to the proof was this fact that the exponent, you see, in Sayre's mass formula, you have to raise, you have to take the sum over all extensions, totally ramified extensions of a given degree of Q, which is the cardinal Q of the residue field, to the power minus C of E over F. So this coefficient, this constant, or this invariant, we had shown that it is the same as the level of our line D. And what was meant by the level? See, there has to be a unique R such that D is contained in UR bar, but not in UR bar, UR plus 1 bar. That's in characteristic 0, or such that D is contained in P minus R bar, but not in the smaller one, not in P minus R plus 1 bar. So this level and the invariant could be deduced from one another. They were essentially the same up to sign, and they can be easily deduced from one another. And that is what helped us count the number of lines of a given level and the contribution that each of those lines made, and then take the sum over all G stable lines, right? G stable lines. For each line, you know what the level is, or for each level, you know how many lines there are because we computed the relevant dimensions, and we know what this coefficient is, and therefore we just need to write down the sum and just sum the series. The series is going to be finite in characteristic 0 here in this case, and it's going to be actually infinite in this case because this R could be any strictly positive integer prime to P. So what we are going to do today is something slightly different. We have finished that topic of Sayre's mass formula. Today, we are going to look at a finite extension L of K. K is still a P field. And of course, this L, or rather the multiplicative group L star, comes with a filtration. OL star, the group of units, then UL1, the group of 1 units, and so on. The higher 1 units. It also comes with a homomorphism, which n star, n L over k, from, of course, L star to k star. So there are these two things which these two structures which L star carries, a filtration and this homomorphism to k star. K star also, of course, has a filtration, right? So the question is, what does this map n L over k, the norm map, what does it do to the filtrations on L star and on k star? These, what does it do to the filtration? So let me give you the rough answer before going into the details. Yeah, so how does n L over k transform the filtration on L star to the filtration on k star? This is a natural question. For example, when we had the upper ramification filtration, we could ask, suppose I have a subgroup, then of course a subgroup has a filtration, the big group has a filtration. What is the relationship between the two? And as far as the ramification filtration, the lower numbering is concerned, the filtration of the subgroup is just the restriction of the filtration on the bigger group. It's just a trace, just the you intersect with the subgroup and you get the filtration on the subgroup. But if the subgroup happens to be normal, then of course there's a filtration of the quotient as well. And how is that deduced from the filtration on the group of which you are taking the quotient? So that is the place where we had to introduce that upper numbering and explain that upper numbering is preserved by the passage to the quotient. So those, for introducing those upper numbering, etc., we had this function psi L over k, right? Which I'll sometimes just simply write as psi for, and this normally UL, this filtration is of course only defined for integers v, but for real v, I now define UL exponent v to be UL, and you just take the integral part of v. It's not the integral part, is the what is sometimes called the ceiling of v, which is the smallest integer larger than v. It's not the largest integer smaller than v, is the smallest integer larger than v. The largest integer smaller than v is called the floor, right? Yeah, this is the ceiling. Now, as I said, the basic results are going to be the following. You, first of all, prove that the norm map takes the group with index, the subgroup with index psi n to the group with the index n. Here it was psi n, and here it is n, right? And it takes psi n plus 1, this thing, to n plus 1. And therefore, we get an induced map. So you get an induced map from this here on the left to the thing here. So that on the left, you have the thing for k. And this map here in between, this map is induced by these, the norm maps, right? These maps. Of course, it will be induced once we prove these two things. Once we prove these two things, we'll get this map and we will identify this map. What does it mean to identify this map? So basically what it means is, here on the left, what is it? It's basically the same as the residue field. This we have seen, right? Similarly, here on the right, it's the residue field of K. Here on the left, it is the residue field of L. So you have to make some choices in order to identify them with the residue fields. And we are going to say that if you make appropriate choices, then you can identify the map on the residue fields which makes this diagram commute, in the sense that, so that computes this map, so to speak. Anyway, so let's get started, and you'll see when we actually come to these things. So even before we go, so as I said, the filtration actually just starts with L star itself. So L star is taken into K star, and OL star is taken into OK star. So this quotient gets mapped to this quotient, and I'll call this map n-1. It's induced by the norm map. So that's one thing, right? I have this map, it exists in nature, the one on the left. But I also have the map VL, which identifies the top group with Z, and I have the map VK, which identifies the bottom group with Z. So now, in order to specify what this map n-1 is, I need to tell you what the map from Z to Z is, which makes this diagram commute. And the answer here is, the map here is FL over multiplication by FL over K. FL over K is, of course, the, let me see if I can, this works, yeah. So F over K, what is it? It's called the residual degree, right? Residual degree of this extension L over K. And similarly, the units are, of course, taken to the units, and the 1 units to 1 units. So I get an induced map N0. On the other hand, the top group is, of course, isomorphic to KL star, the multiplicative group. This is the multiplicative group of the residue field. And the bottom group gets identified with the multiplicative group of the residue field of K. So I need to tell you what is the map from, what is the map here, this vertical map, which makes this diagram commute. And the answer is, you first take the norm from this to this, right? This is also an extension. You have the extension KL over KK. It's of degree FL over K, right? That is the degree of this extension here. And you have the norm map on these residue fields. It's not, I'm calling it new. So it's not new which makes its diagram commute. It's new of whatever you're taking, and you raise it to the power EL over K, where EL over K, of course, is this E here. It's the ramification index of L over K. So these are the statements, 1 and 2. I have to show that these two things, these two squares commute. Okay, so here, what are the hypotheses? K is a P field, and L over K is a, what is it? It's just a finite separable extension. Now, the first observation we make is that you don't need to prove 1 and 2. I mean, okay, you don't need to prove it for all finite separable extensions. You just need to prove it for 2 types of extensions. Namely, either you can assume that L over K is unramified, or that it's totally ramified. Why? How can you assume that? That's because any finite separable extension can be sort of written as an unramified extension followed by a totally ramified extension. So suppose I know how to prove it for totally ramified extensions and for unramified extensions. So from these two cases, can I deduce the general case of L over K? And the answer is, of course, yes. That is just by transitivity. Everything which appears in this statement, in the statement of the proposition, is transitive, in the sense that so what does that mean? Let me be very explicit. Let me just do it here. Maybe if I have M, L, and K, by transitivity, I mean that the norm map from M over K, that's equal to the norm from M to L. You first apply this one, and then you apply the norm map from L to K, right? So this is what I mean by transitivity for the norm map. But you also have transitivity for F, the residual degree. This is equal to F M over L times F L over K. And similarly, E M over L, M over K is equal to E M over L times E L over K. So because of these transitivity relations, you may assume that L over K is either unramified or it's totally ramified. Now, if it's unramified, then it's actually cyclic of degree equal to the residual degree. I take a uniformizer of my P field K, then it continues to be a uniformizer of L, right? Because when I write Pk, normally when I write it as a power of a uniformizer of L, I get, if I have a uniformizer of K and a uniformizer of L, then pi K is equal to U, where U is in OL star, times pi L to the power EL over K, where EL over K is the residual degree. But if it's unramified, that just means that EL over K is equal to 1. So that means that pi K is U times pi L. Whatever uniformizer pi L I have chosen differs from this by a unit. So this is itself a uniformizer of L. And what's the norm of this uniformizer? Of course, because this belongs to K, when I take norm L over K, it'll get multiplied by itself as many times as the degree indicates. So the norm is pi K to the power FL over K. And that's exactly what the first square here is saying. The first square here says that, in order to show that this square commutes, I know that this is isomorphic to Z, so I can take a generator of this. A generator is nothing but a uniformizer of L, but because L over K is unramified, I can take a uniformizer of K as a uniformizer of L, and this I know goes to pi F to the power, not pi F, what is pi F? Goes to pi K to the power FL over K. And that's it. Here the generator is 1, here it's multiplicative, this is multiplicative notation, and here it's additive notation. So 1 goes to FL over K times 1, right? That's what. Okay, let's come to the second part, the second square. For the second, we write the units of L as the units of the residue field, and then the times the 1 units, and similarly for the units of k, we write them as the units of the residue field times 1 units, right? We have these identifications. What we also know is we are still assuming that L over k is unramified, right? And we are looking at the second square. But, okay, so because it's unramified, the Galois group of L over k is the same as the Galois group of the residual extension. It's this natural map from this Galois group to this Galois group here is an isomorphism. So take an element x in OL star. So it's some unit, this is an OKL star times a 1 unit. And let's just compute the norm. The norm by definition is the product of all conjugates. And G is the Galois group. So as S runs through the Galois group, Sx runs through all conjugates of X. But this X, I've written it as this product. So I'll get this product times this product. Now this product, the first product is, what is it? Here it's nu of x bar. The nu is just the norm map from KL to KK, right? Because it's the product of all conjugates of x bar. So it's the norm of x bar. And the second one is certainly nu k1 because x1 is in ul1, and so this product is in ul1, and you can check that the norm map takes 1 units to 1 units. In any case, we are working modulo 1 units here, right? Look at the second diagram, modulo 1 units. So basically, we have shown that the second square commutes because what have we done? We have OL star modulo U1 UL1. That is really the same as KL star. And then you have this norm map, which was called N0 perhaps, to OK star modulo UK1, which is isomorphic to KK star. And I have to say, what is this map? What is the map here, which makes this diagram commute? So that, then I can, if I identify this map, then I can say that I've understood what N naught is, or computed what N naught is. And we have seen that this is just the norm map from KL star, okay, to KK star. But you might complain that the second square here had not only the norm map, but this exponent, which is the ramification index. And the answer is here, there is a ramification index here as well. Here, it's 1. So it's just the norm map. It's just you can write it as, this is the ramification index. Okay, so now let's look at the case where L over K is totally ramified. And you have to, so totally ramified means that the residual degree is 1 and the residue fields are the same. Now take a uniformizer of L. We have seen that the norm of that uniformizer is a uniformizer of K. Did we see this? Yes. We showed that whenever you have a totally ramified extension and a uniformizer of the big field, then its minimal polynomial is an Eisenstein polynomial. And the constant term of the minimal polynomial is the norm of this by L over L. norm of pi L, and also because it's the constant term of an Eisenstein polynomial, it is divisible by a uniformizer of k, but not by the square of the uniformizer. So it is a uniformizer. Okay, so that already shows that the first square commutes. Okay, what have we shown? We have shown that if I have L star modulo OL star to K star modulo OK star, then you have VL, which takes to Z, VK, which also takes to Z. Then you have some map here, which you need to identify. And this map is called N-1. And we are trying to figure out what it is. Now, here, the generator, pi L bar, or the image of a uniformizer, is going to be a generator here. What does this generator go to under the norm map? It goes to norm of L pi L bar. But this, as we have said, is a generator of K star modulo OK star. So a generator here goes to a generator here, which means that this is an isomorphism. We wanted to show that it commutes, the first square commutes with FL over K here, but you do have FL over K here, because FL over K is actually equal to 1 in this setting, because we are assuming that L over K is totally ramified. So that's it. I mean, this is the identity map. Okay, so the first square commutes. How about the second one? Now, every element here has a representative X in OK star. Why is that? Because what I mean is that, okay, all I mean is the following. OL star, you have this quotient KL star. Inside this, you have that was OL, this is OK. And here you have K star. But these things are equal. They're the same, because we are looking at a case where KL is equal to KK. So if I take an element here, I take its representative. I want to show that every element here has a representative in OL star, which actually belongs to this. And that's clear, because taking an element here is the same as taking an element here, because these two are the same, right? And this, of course, has a representative here. That's it. So that's every element in this has a representative in OK star. And what is the norm of this? Of course, norm of this is x to the power EL over K. Why? This is obvious, because norm is the product of all the conjugates, and all the conjugates of x are equal to x if x belongs to OK star. And how many times are you taking? So, okay, I mean, norm of L over K of x is actually equal to the product for S in G of S of x. So this is equal to the product S in G of x, because S of x is equal to x, and this is equal to x to the power E L over K, because that's the number of elements in the group G. Or, oh, wait a moment. Well, it's not a Galois extension. It's not a Galois extension, so you have to be slightly careful. Maybe you go to a Galois closure, or, I mean, even if it's not a Galois extension, we know that if you have a finite separable extension, L over K of degree D, or maybe I should use a different notation. It's not the same, it doesn't have anything to do with P fields. I'm saying if you have a field F and a finite separable extension E of degree D, and then you look at norm E to F of an element X which is in F, then of course that's equal to X to the power D, right? So that's what is being used. So that's what it is. So now this diagram commutes. Which diagram? Yeah. So the diagram, which diagram commutes now? What have I proved? I've proved that this modulo U1, or rather UL1, this is isomorphic to KL star. Then you have the norm map N0 is perhaps a good name, taking you to OK star modulo UK1, which is isomorphic to KK star, and these two things are the same. So the map here, which makes the diagram commute, is raising to the power EL over K. That's what we have proved. But in the second diagram, what we had to prove is that the map is not just raising to the power EL over K, but first take the norm and then raise it to the power EL over K. But that's what it is, because here the extension is trivial. So it's this extension is, it's an equality. So norm L over, or rather KL over KK is the identity map of, you want to call it KL or KK because they are the same. Okay. So at this point, I have to shift to a different file. Okay. Okay. So in a sense, we have seen what the norm map does to at the level of this L star. Yeah, see, that's the problem why OL star. And now let's see what it does at the level of UL1. What does it do to these other things? These things we have just seen. Okay, so now let's look at the 1 units and higher units. And first, let's consider unramified case. So we have a finite, what do we have? We have an extension L over K. K is a P field. L is a finite unramified extension. So unramified extensions being cyclic, we have a Galois group, which is cyclic. And the proposition says that if this is unramified, as I'm assuming, then the norm, I'll just write N sometimes, for N L over K. So this is actually N L over K. So the norm map here takes UL, the nth group here, to the nth group. The indexing remains the same. That is the content of this proposition. So for every n equal to, for 0 we have done it, greater than or equal to 1 is what we wanted to say. So let's prove this. So every x in this here, x will look like 1 plus y, where y is PL to the n, right? The same n is here. Then it's a Galois extension, and I take an element S in the Galois group and apply it to x. So S of x is going to be 1 plus sy, because S, of course, is an automorphism of the field L. So it takes 1 to 1, and it takes y to s of y, of course, right? So this is what I have for all s in G. And the norm, which is the product of all these conjugates, therefore is going to be equal to the product of all these 1 plus sy's, where s runs through G. Now when I expand this product, when I expand it, I'll get 1 by choosing 1 from each of the factors. I get this one. Then if I choose 1 from each factor except one of the factors where I pick up this term, then I'll get sy, and some other factor I'll get ty, where t is some other element of G. So I'll get sx plus, I'll get sy plus ty, meaning I'll get the summation over all s in G of sy. That's when I pick up just one element in each of the factors which is different from this one. Then I can choose 2 of them, etc. But when I choose 2 such things, this y is already in PL to the n. And sy is, of course, also in PL to the n, because s respects the filtration. So sy times ty, where t is another element of G, that is going to be in PL to the power 2n. If I have 2 such things. So if I'm going modulo PL to the power 2n, then I can write the norm of x as just 1 plus this thing here. Okay. Now, what is PLn intersected with k? It's pkn. This doesn't happen in general. It happens when L over k is unramified, which it is here. So, how about this term here? This thing is in PLn intersected with k, this sum, because each of the terms is in PLn, so the sum is in PL to the n, and it's the sum over all conjugates, so it's also in k, and therefore it's in pkn. So if I were to go modulo pkn, I'll get norm of x is equal to 1. This means that, this is just in order to say that, that proves this statement. It takes uln to ukn, right? This statement here. And therefore, it'll of course take uln plus 1 to ukn plus 1, or I here, I've used the notation now. And therefore, there's going to be an induced map. And we now are interested in finding out what this induced map is. We have already seen that at the level of U0, this is N naught, and it was the norm map that we have seen earlier, right? Here the notation is, the notation is UL0 was called OL star earlier, and of course UK0 is OK star, right? So when we prove this, we proved, that file is gone. So that was when we proved that OL star modulo UL1, this was isomorphic to KL star, and you had the norm map, which was called N0, taking you to OK star modulo UK1, which is isomorphic to K star. And the map here was just the ordinary norm map at this level. Remember, in the unramified case, yes. That was when this I here is equal to 0. What happens when this I is some higher, some integer which is greater than 1. It's called n for some reason. Okay, so you will get this induced map nn because this uln is taken to ukn and this one is taken to this one here. So you get this induced map nn. On the other hand, I have this isomorphism and this isomorphism. If I choose pi k, if I choose a uniformizer pi k of k, this is also a uniformizer of L because L over k is unramified. So every element of this quotient here, uln modulo uln plus 1, is the image of 1 plus a times pi k to the n, and this a isn't pi l or isn't ol. Okay. Similarly, here on the right, every element is the image of 1 plus a pi k to the n, except that here, of course, the a has to be in OK. So if I've chosen a uniformizer pi k, then pi k to the power n is, or rather, I mean, I get an isomorphism like this, which takes an element like this, 1 plus pi k to the n bar to just a bar in kl. And similarly here, it takes 1 plus a times pi k to the n to a bar. Of course, a bar will be in kk, and here a bar is going to be in kl, because this a is in pi l, and here the a is in ol. So, you see, this horizontal map is the one, no, it's not. It's a, well, I don't know whether it's an isomorphism or not, right? This is a map which I want to understand, NN. And if I say that it's the same as the trace map, I mean, if this diagram commutes, then it amounts to saying that it's really the same as the trace map when I make these vertical identifications. So as I said, for n naught, we have seen this earlier. For nn, the maps which I've explained just now, it follows from what we have proved in the previous proposition. Now, right, yeah. Why does it follow from the previous proposition? It follows, it's the presence of this thing here. Because this is basically the trace S L over K of Y. That's the crucial thing here. If x is 1 plus y, then S of x is 1 plus sy for all s, and the norm of x is going to be the product of all these things, but the product is 1 plus the trace modulo higher powers. So those higher powers will disappear so if something is true modulo PL to the 2n, then of course it's going to be true modulo PL to the n plus 1 also, right? Because n plus 1 is strictly less than or equal to 2n, right? Our n is strictly positive, so you have this. And this intersected with k, yeah, see, that was a problem with my pen, so is equal to pi k to the n plus 1. So that's what, where is it? So maybe it's written down here. See, how does it? So in the This is the square. It has been overwritten so many times, but here is the thing. This is the what n, little n takes it to. Under the isomorphism, it goes to a bar in KL, and under this vertical isomorphism, it's taken to this in KK. So you can see that this is this element here is the trace of this a bar, because it's all it's the sum of all the conjugates of a bar. So it follows from this that the norm map takes UL is surjective from ULN to UKN. The image of ULN under the norm map is UKN. And moreover, if I look at K star modulo N K L star, then the valuation gives me an isomorphism with Z mod Fz, where F, of course, is FL over K, right? That is, and it's equal to L over the degree of L over K, because by hypothesis, L over K is unramified. This is. So these things are actually formal consequences of what we have done, and the fact that the norm map and the trace map are surjective. So let me elaborate a little bit. In what sense is it a formal consequence? So that involves a purely algebraic lemma, and it says that if I have a homomorphism of, let's say, commutative groups, which are filtered, which means that, this A0 is A and B0 is B, and the map F is from A0 to B0, but it takes A1 to B1, A2 to B2. So A has a filtration, it has a subgroup A1, which is a subgroup A2, and so on. B has a filtration given by subgroups B1, B2, and so on. And the map F is a map of filtered groups, in the sense that it takes A1 to B1 and A2 to B2, and so on. So that's one of the things which is given to me, a map of filtered groups. And the hypothesis is that A is the inverse limit of A modulo AN. Also, B is the inverse limit of B modulo Bn. But of course, another consequence of this, the fact that it's a map of filtered modules, filtered groups, gives you a map Fn from An modulo An plus 1 to Bn modulo Bn plus 1. This is what we are doing for, this is abstracted from, the map that we should keep in mind is the norm map. We have proved that the norm map so we have proved that the norm map takes L star to K star, of course, then OK star to O, it's not OK here, it's OL. OL star to OK star takes UL1 to UK1. Yeah, I'm sorry, the pen doesn't work properly, but you understand what is going on. So, so that was the hypothesis, that A is the inverse limit and B is this inverse limit. Here is of this system, and A is the inverse limit of this system. Then the conclusion of the lemma is that if each of these Fn's, these maps, if they are injective for every n, then F itself is an injective map. And similarly, if all these fn's are surjective, then f itself is surjective. And apart from this lemma, I need the snake lemma in order to conclude these two facts from what we have proved earlier. So I'll stop for 2 minutes to see if there are any questions. Okay, so let's continue. So I've mentioned these two lemmas. Actually, I'm being very slow today. So I've done the unramified case. Now I'm going to do the totally ramified case. You see, by transitivity, everything needs to be done only in these two cases, when the extension is either unramified or totally ramified. Of course, in general, an extension is neither unramified nor totally ramified. I mean, it has some ramification and it has some residual extension as well. So, okay, so let's come back to our P field K and take a finite R. We are taking a totally ramified extension which is cyclic of prime degree. So there's a Galois group and the order of the group is L. L is some prime. Doesn't have to be the same as this prime P. It could be different. So G is a cyclic group, we know, because whenever you have a oh, well, it's a group of prime degree, so this has to be cyclic. And now there was this unique ramification break for this extension. What is that? That's the integer t such that g is equal to gt, but gt plus 1 is trivial. G doesn't have many subgroups. I mean, it's a group of prime order, so the only subgroup is a trivial one, and of course the whole group itself. So these ramification subgroups, they will have to be equal to the whole group up to a point, and then equal to the trivial subgroup. That point is called the unique ramification break, and I'm calling it T here. And recall that the function psi, in this case, is just given by psi L over k of x is equal to x if x is less than t, and it's t plus L times x minus t if x is greater than t. Now, this is something which follows immediately from the definition of this function psi. Also recall that the exponent of the different, I mean, we have the different of L over k, right? And the exponent in this case can be computed from the unique ramification break. It's t plus 1 times, it's not t minus 1, yeah, of course. So how do I correct this? Let me use this thing here. This is L here, not t. It's t plus 1 times L minus 1. So the first lemma is that if I have an ideal of OK and an ideal of OL, then the trace maps takes this ideal B into the ideal A, if and only if this ideal B is contained in A times, I mean now A is being viewed as an ideal in OL, A times the inverse different. It's the, so that's what the statement is. The trace of an ideal B of OL is contained in an ideal A of OK, if and only if B is contained in A times the inverse different. This is more or less by the definition, perhaps. So here's a proof. You look at the left-hand side. The left-hand side holds, I mean, this inclusion holds if and only A inverse times, you take A inverse to the other side, so to speak, is contained in OK. Now, but of course, the trace of this map is, the trace map is OK linear, right? So this A inverse outside can be taken inside, so to speak. And so the trace of this ideal should be contained in OK. And the trace of an ideal is contained in OK if and only if that ideal is contained in the inverse different. And this can be rewritten as the right-hand side. So it's more or less by the definition. So, and the property of the different or rather the inverse different, dl over k is called the inverse different. And if C is an ideal, let C be an ideal, and the property of this inverse different is that the trace map from, the trace map takes this C into OK, into the integral elements, if and only if this C is contained in the inverse different. So in other words, this is the largest ideal which is taken into OK by the trace map, L over K. Okay, so that does a small lemma. Then you have this somewhat slightly more interesting lemma, which says that the trace of PL to the n, that's an ideal of OL, right? PL to the n. And the trace is OK linear. So the image of this ideal has to be an ideal of OK. And here it says that the ideal is pk to the power r, where r is given by this formula. R is the integral part of m plus n over L. N is this n. M, what is m here? M is the exponent of the different. This is m. So it's just t plus 1 times L minus 1. Except that, no, I'm not in this special case. The exponent of the different is this. Okay, I'm proving it only in this special case. So you have this exponent of the different. It's equal to 1 plus t times L minus 1. Okay. Now, so here's the proof. I have to prove that the trace of PL to the n is equal to pk to the r, where r is given by this expression. Now the trace is OK linear. So of course, the image of PL to the n is an ideal in OK. And if r is an integer, when is the trace contained in pk to the r? That is the case if and only if this thing is contained in pk to the r here times the inverse different, right? Here, so we are replacing this OK by some p to the r. So we can do this. You can replace this OK by some p to the, to the r, but then you have to write p to the r, pk to the r here as well. Right. So this here happens if and only if p to the, this is pl to the n, right? And what is the thing on the right hand side equal to? It's equal to this. Because we know what the exponent of the different is. And therefore, I mean, this, and that's exactly what we wanted to prove. I mean, so it's going to be contained in p k to the r if and only if this r is less than this, which is the same as saying that r is equal to this. Okay, so that proves this lemma. And the next lemma is really important. It says that if I take an x which is in PL to the n, right? Then this 1 plus x is, of course, in UL to the n, and I take its norm down to k, then I'll get 1 plus the trace of x times plus the norm of x modulo something, modulo this thing here. And what is this thing? Modulo the image of the ideal PL to the 2n. This n, and here it's 2n. It's this n. Okay, so let's prove this. So by definition, the norm of 1 plus x is, of course, the product over all s in G of 1 plus sx. We are still in this case, right? What are the hypotheses on L and K? The hypotheses are that K is a P field, L is a totally ramified cyclic of degree L, and L is prime. That's the hypothesis. Then the claim is that the norm of 1 plus x, if x is in PL to the n, is 1 plus trace of x plus norm of x modulo the trace of the ideal PL to the 2n. Okay, so the norm is equal to the product of the conjugates. And now again, I have, you see, the product of all these things over S running in G. So if I take 1 from each of the factors, I get this term here. If I take 1 from all the factors except 1, then I'll get this term here. Because it will be the sum of the conjugates of x, which is the trace of x. If I take 1 from none of the factors, then I get this term here, because it's the product of all the conjugates of x, and that's the norm of x. But of course, these are these are not the only two possibilities, that you take 1 from all but 1 and 1 from none, and there are intermediate possibilities, right? You take 1 from some of the factors and s of x from the remaining factors. So s of x from 2 or more factors. I mean, if you take it just from 1 factor, then this is accounted for. So this is what the notation is. It'll be the product of all these s of x, where a is some subset of G, right? Such that the number of elements in A is at least 2 and not equal to the whole of G. I mean, because if it's equal to the whole of G, the term is here. So here are the terms which correspond to other possibilities. And this sum is empty, of course, if the order of the group itself is 2, because so if L is equal to 2, there are no subsets, no A's. So the term is, this sum is empty, and therefore so you have actual equality in if L is equal to 2. Now, if the order of G is different from 2, then you see all these A's, they don't come by themselves. I mean, the group G acts on this kind of subsets, and each orbit for this action has L elements. Okay, this is something that I can verify. And the sum that you want to compute here it can be written as the sum over all orbits, and then you take A in the orbits, and then you take S in the A's of these Sx. Now, when you look at the innermost product, this is S in A of Sx each, and there are at least two S's in A, right? Because the order of A is at least 2. So, and each X is in P to the N. So, when you take the product of 2 of them, you will be in PL to the 2n at least. Then you take the sum of these things. So you will still be in this. And when you take the sum over all, wait a moment. Yeah, when you take the sum over all A's in this, in the orbit, in the same orbit, then you'll get the trace of this. Right? Okay. And therefore, I mean, that's exactly what we had to prove, that you'll get something more in. This is the expression modulo the trace. Okay. So now, whenever you have two primes, I mean, it's always simpler when the prime L is different from the prime P, and that's the tame case here. So L over K is totally ramified, but it's tamely ramified. And the proposition says that, of course, in that case, you have this map theta naught from G naught modulo G1 to KL star, right? But G naught is equal to G because it's totally ramified, and it's tamely ramified, so G1 is trivial. So this G naught modulo G1 is actually equal to G, and theta 1 is an embedding of G into KL star. It's an injective map, right? So the theta is injective. We have seen this by construction, and the proposition says that it's equal to the kernel of raising to the power L map on KL. It's KL, but KL is equal to KK is the same thing, right? Because we are totally ramified, right? So theta naught is injective. G has order L, so SL to the power 1 is 1 for every S in L. So theta of SL, S to the power L is equal to 1, but that's theta S to the power L is equal to 1. So what it says is that this composite is the trivial map. In other words, the image of the map theta is contained in the kernel of the raising to the power L map. But I mean, these two groups have the same order. They have the same order. Why do they have the same order? I mean, the order of theta is injective, so the order here is L, and the kernel here, this also has order L because this KK star is cyclic of order a multiple of L. Because why is it a multiple of L? Because this we have seen in the classification of tame extensions of P fields, that if it's a cyclic extension of degree L, then the multiplicative group of the residue field has an element of order L. So that's what. And so these two groups are the same order, and one is included in the other, so they are actually equal. So let's continue with the tame case, and let E be the ramification index. So we are abandoning this cyclic of prime degree case. We are taking an arbitrary extension, which is totally but tamely ramified. We are no longer requiring it to be of prime degree. It could be of any degree E, which is EL over K, which is short for EL over K. But of course, it has to be prime to P because we are looking at tame extensions. So take K to be a P field, take L to be a finite, tamely ramified, totally but tamely ramified extension of K of degree E. Now, the proposition says that psi L over K of n is n times E for all integers n. And the norm map takes UL En to UK n, En here, and En plus 1 here, and n plus 1 here. So you, of course, will get a map on the, you get an induced map here, and n is induced from these two inclusions, this and this. But of course, we also have isomorphisms here. Once you choose some uniformizers and so on, and here you have, so what is the map here which makes this diagram commute? And the answer is that you take the, if you take the identity map, then this diagram commutes. And the final part is, so I'm a little confused because normally you have to, in order to take these isomorphisms, you have to choose uniformizers, and I wonder whether, I mean, this cannot continue to be identity. So it says for suitable generators, right? Then it's okay. For suitable generators of these things as OL and OK modules, you'll get these isomorphism. So you can choose as generators for this and this, such that the isomorphisms given here commute with the identity map here. Okay, and the final thing is that if M is prime to the ramification index, then ULM is taken, has the same image under the norm map as ULM plus 1. Okay, so let's try to prove this. So we have to prove it for all totally but tamely ramified extensions. As before, by transitivity, we may assume that E is actually a prime number L, because every tamely ramified Galois extension, no, wait a minute, what is this? No, we are not using Galois anywhere, that's right. So, but we know that every tamely ramified, totally but tamely ramified extension of P fields can be obtained as a succession of totally tamely ramified extensions of prime degree. And of course, the prime is different from the prime P. So let's look at just one of those stages. You have some extension of prime degree L, which is totally ramified. L is different from P. And in that case, we know that the different is going to be PL to the power L minus 1. And that the exponent of the different is L minus 1. Okay. We'll also call it M. Now, if X is in PL to the Ln, then the trace of X is in Pk to the N, where N is given by this. No, because no, N is. So the proof is that we have already proved something about where the trace maps take the filtration on the additive group, and this kind of thing had appeared there. So it's just a straight application of that statement. But the norm map takes x to pk L times n, because normally the norm map is the product. Okay, I mean it'll. So normally it will take it to this product, but when you intersect with k, and this is the ramification index, so you'll end up with this here. So the norm of 1 plus x is 1 plus the trace, and there was a norm term as well, but the norm term disappears because we are going modulo p to the n plus 1, pk to the power n plus 1. Here it's L times n, right? Which is L times n is greater than n plus 1. If L is, yeah, okay. If L is 2 and n is 1, then maybe I should put equality here. Yeah. Yeah, but all I need is equality. I mean, well, all I need is a loose inequality. Not a, I don't need a strict one. Anyway, so the so the rest of the proof, I mean, once we have this, I'm going to skip the details here. You just take some OL basis of this OL module, then the trace of that thing is going to be an OK basis of this here. And every element of this can be written in this form where A can be taken to be an OK. I mean, normally you would think that A is an OL, but it suffices to take it to be in OK because KL is equal to KK. It's totally ramified. And finally, you need to use the fact that the trace map is OK linear. So when you use all this, you get what we wanted. You get the commutativity of this diagram. And this also you can just try to prove it. Okay, so this is the meat of the whole talk today. This is the wild case when L is equal to P. So you have a totally ramified extension of degree P. You still have G as the Galois group. Now the unique ramification break will be at least equal to 1. I mean, at least it will be greater than 1. It cannot be 0. It is 0 only when L is different from P. Yeah, it's strictly greater than 1, 0. And recall that the map P L over K is equal to N if N is in this interval, and it's equal to this if N is strictly superior to T. And the proposition says that UL Cn, so Psi is short for Psi L over K, UL Cn is taken by the norm map to UKN, and the next one is taken to the next one for all n which are strictly positive. Okay, so once you have these two things, you get an induced map here, vertical map on the left. But this top thing is isomorphic to KL and the bottom thing is isomorphic to KK. And of course, these two are equal, but it's not with equality that the diagram commutes. It commutes with maybe, F is confusing. So if you, let's call it phi. Or phi is also confusing because phi is already in use. So let's continue to call it F, it's okay. It commutes with the map Fn, where Fn is raised into the power P if n is strictly smaller than T. It's P beta, if n is equal to T, where P beta is given by P beta of alpha is alpha to the power P minus beta times alpha, where beta is going to be a certain element in K to the power, Kk star to the power P minus 1. And finally, this Fn is equal to the identity map if n is strictly greater than T. That is just the first part of the proposition. The second statement says that this sequence is exact. What is the sequence? You have the Galois group here. And remember that theta t takes gt modulo gt plus 1 into this group. But in our case, gt is equal to g and gt plus 1 is trivial. So this quotient is actually equal to g. So theta t takes g into this quotient. And of course, this is the map n sub t. So this sequence is exact, where t is not arbitrary, right? T is equal to the unique ramification break. T is the ramification break. And finally, I mean, if this m is some integer which is prime to p, then L exponent t plus m is taken by the norm map. The image under the norm map of UL to the t plus m is the same as the image under the norm map of UL to the t plus m plus 1. See here, this Cn and Cn plus 1 don't have the same image. The image of the first one is contained in this, and the image of the second one is contained in this. Because n is, wait a moment. Yeah. Yes. Yeah, okay. So in this, if here these are multiples of p. Here you are taking something which is not a multiple of t, right? So if it had been a multiple of t, then we know, because it's psi n, etc. So we know what happens, you know. We have determined these maps. Okay. So everything is based upon that lemma, which we had proved. I mean, roughly, yes. So the lemma was n L over k, 1 plus x is congruent to, so if x in PL to the n, then this is 1 plus SL over k so it was 1 plus SL over k of x plus n. So this S is the trace, of course, plus the norm of x modulo SL over k of PL to the 2n. So that this is the lemma, which is very useful. We have proved it earlier. So we are going to use it again and again. And let's come to the proof of this proposition. So first take n to be in this interval 1 to t, right? This case here, n is strictly less than t. Then if x is in PL to the n, then the norm is in pk to the n, and the trace is in pk to the r, where this r is given by this formula and m is equal to this, the exponent of the different. Now the claim is that this r is greater than n plus 1. I mean, this you can just check, right? I mean, everything is so explicit. So this trace is going to be in r is greater than n plus 1, so the trace is in pk to the n plus 1. And similarly, this is going to be contained in this. So this, what does it reduce to? This formula reduces to this modulo pk to the n plus 1. Right? And now, if I just take an OL basis of PL to the n, call it pi, then its norm, of course, is an OK basis of pk to the n. And every element of this can be written in this form, where A is an OK because KL is equal to KK. Now, when I take a norm, the norm of such an element, I'll of course get 1 plus A to the power P times pi. So this pi is, yeah, exactly. It's this pi. Modulo this thing here. So that's exactly what was. We proved that this thing commutes with here, the map is alpha going to alpha to the power p. This is the power p here. Okay. So we have proved the case n in the interval 1 to n is strictly less than t. Here is the case n equal to t. So it's the same formula which we are using, this formula here, right? But here, now, yeah, it's slightly, the slight difference here is that, okay, I've not too much time, but let me say it quickly, that if I take a basis, OL basis of PL to the T, T here, then both its norm and its trace are OK bases of PK to the T. So I'll take the norm as a basis, and I'll express the trace as a multiple of the norm, of course, by a unit. And then that formula here, right, this formula here, this becomes, this becomes this formula, modulo this. So the square commutes with this beta, and and finally the case when n is strictly greater than t is similar, and here I have written it out and says that, so I know that C of n in this case is E given by this formula, and if x is in PL to the Cn, then the trace is in pk to the n, but the norm is in pk to the Cn, but that's containing pk to the n plus 1, because Cn has this expression, right? So the norm, if I go modulo pk to the n plus 1, then I'm just left with 1 plus the trace of x. The norm of 1 plus x is congruent to 1 plus the trace of x modulo pk to the n plus 1. And so I get an induced map here. This is n induced from the norm map. And I have these vertical isomorphisms coming, not vertical, horizontal isomorphisms, which are coming from and by choosing some bases, appropriate bases for the ideals, and then this diagram commutes with some, I mean, here, of course, this KL is equal to KK. So you have a KK linear map, but a linear map from a one-dimensional space to itself is multiplication by some scalar. Can that scalar be 0? If it was 0, then that means that this map is 0, right? Because here you have these horizontal isomorphisms, and that would mean that the trace of PL to the Cn, and the trace of this here would be pk to the n plus 1. I mean, that's what it means for it to be 0. But that contradicts the lemma on page 11. So on page 11, what is the lemma we had? We had this lemma which told you that the trace of PL to the n is in pk to the r, where r is this expression. It cannot be contained in the image of the trait of this PL to the n is equal to this. So it cannot be contained in a smaller one. And that is the end of today's lecture, right? Are there any questions? Yeah? No questions? So I'll end this session today, and we'll meet on Wednesday.